So let's do another example. Let's say we wanted to solve the system of equations 2x plus y is equal to 6, and 3x plus 4y is equal to 4. Now in the previous example, one of our equations already had an isolated variable. We don't have that luxury with this example, but if you look, y would be pretty easy to get by itself. It doesn't have a leading coefficient attached to it. Well, it does, it's 1. Doesn't have some other value as its leading coefficient. So let's get y all by itself. We'll move that 2x over to the other side of its equal sign. We can rewrite this system of equations as y is equal to negative 2x plus 6, and this bottom equation we'll leave alone. 3x plus 4y is equal to 4. Once we've gotten one variable all by itself, we know what y is. Let's plug it in to the bottom equation. That means when we had 3x plus 4y being equal to 4, we can rewrite this equation as 3x plus 4 times negative 2x plus 6 equals 4. All we've done was replace y with it in terms of x's and constants. So now we'll distribute that 4 across addition. Get 3x. 4 times negative 2x will give us a negative 8x, and then 4 times 6 gives us a positive 24. That's equal to 4. We can gather like terms. Negative 5x plus 24 is equal to 4. Isolate some variables, or isolate the variable. Negative 5x is equal to negative 20, almost there. Divide by negative 5, and we see that x is equal to 4. Now that we've got x all by itself, like I said before, it doesn't matter which equation we plug x into, but this top equation is already set up to kick us out a value of y when we give it a value of x. So we'll use that top equation. We know that y is equal to negative 2 times x plus 6. We know that x is equal to 4. That means y has to be equal to negative 2 times 4 plus 6, or y is equal to negative 8 plus 6, or y is equal to negative 2. So that means the point, and remember solutions to systems of equations are points, the point x, y, that makes both of these statements true, or you could think of that as the point of intersection of these two lines, is the point for negative 2. And we can always double check our work. So let's go back to that top equation. We want 2x plus y to be equal to 6. We said that x was equal to 4 and y was equal to a negative 2. We want to know, is that equal to 6? Well, 2 times 4 gives us 8, plus a negative 2 is the same as minus 2, equals 6. Yeah, 8 take away 2 is 6, because 6 is equal to 6. Our bottom equation, we want to know if 3x plus 4y is equal to 4, or we want to know if 3 times 4 plus 4 times negative 2 is equal to 4. Well, 3 times 4 is 12. 4 times negative 2 is a negative 8 equals 4. We're making sure this is true. And we go, yeah, 12 minus 4 is equal to 4. 4 is totally equal to 4. So again, we took this system of equations. It wasn't, we didn't have a variable all by itself, so we solved one of the equations to get one of the variables by themselves. Technically, we could have solved for 2 in this top, x in this top equation, or we could have solved for either variable in the bottom equation. I tried to choose the path of least resistance, solve for y, required the least work, so that's what we did. Once we got one of the variables by itself, we plugged this equation, we substituted it in, into the bottom equation. When we had 3x plus 4y is equal to 4, now we have 3x plus 4 times the quantity of negative 2x plus 6 is equal to 4. We distributed, we gathered like terms, we solved for x. Once we had x all by itself, it did not matter which equation we plugged it back into. Either of them would have given us the correct answer. We chose this top equation because it was a little bit easier to work with. Y is equal to negative 2x plus 6. Well, x is 4. We plugged that in for x, solved for y, got y is equal to negative 2. The important part, not necessarily the important part, but the part for good measure, we checked our work when we were done to make sure it checked out. So, if you remember from last time, solving systems of two equations with two variables is a question about lines. We can either have a pair of lines that intersect in some location that gave us one solution. We could have two equations that gave rise to parallel lines. That would be no solution. Or we could have two equations that turned out to give rise to the same graph. And that was infinitely many solutions. We've done a couple examples of one solution so far. I want to give you an example of no solution and infinitely many solutions so you know what to be on the lookout for. So, let's start off with y is equal to negative 3x plus 5 and y is equal to negative 3x minus 2. Right off the bat, if you notice that these two are lines, they're lines that have the same slope. Lines with the same slope are parallel. That means they're never going to intersect. So you don't have to proceed from this point if you make the observation that they are parallel lines, but let's say you didn't notice that. Let's say you continued with the method I've outlined in the previous examples. And let's say that, well, this bottom equation is solved for y. They both are, but let's take this bottom equation and plug it into the top equation. That top equation says that y needs to be equal to a negative 3x plus 5. That bottom equation says that y is equal to a negative 3x minus 2, which still has to be equal to negative 3x plus 5. Well, let's add 3x to both sides. And this equation breaks down to saying that negative 2 is equal to 5. It's most certainly not. When you do the method of substitution, and after you do the substitution step, if you will, and you try and get your variables all by themselves, and what you're left with is a false statement. False statements mean that there's no solution. So you get negative 2 is equal to 5, 1 being equal to 0, 3 being equal to, I don't know, 17. Anytime when you have some number equal to, say, a different number, different colored number, a different number, that's no solution. On the other hand, let's say we had the system where x is equal to 2y minus 1 and 4y minus 2x is equal to 2. Well, this top equation is already set up. We know what x is equal to in terms of y's and constants, so let's take this top equation, plug it into the bottom equation. We had that 4y minus 2x is equal to 2, but we know what x is now. So let's perform this substitution. 2y minus 1 is equal to 2. And now let's solve for y. We'll take this minus 2, and be careful because that minus sign is along for the right. And we'll distribute it across substitution. Get 4y. Negative 2 times 2y will give us a minus 4y. And negative 2 times a minus 1 gives us plus 2. And that still has to be equal to 2. If we gather these like terms, 4y take away 4y doesn't leave any y's around, and we're left with 2 is equal to 2. We have a true statement. Whenever we get true statements that are true regardless the value of x, that means there are infinitely many solutions. So, to recap, false statements, no solutions. True statements, infinitely many solutions. So the last thing we're going to do is go over a story problem. So, the architects who designed the John Hancock Building in Chicago created a visually appealing building that slants to the side. The ground floor is in the shape of a rectangle that is larger than the rectangle formed by the top floor. The ground floor has a perimeter of 860 feet. Ground floor has a perimeter of 860 feet. And we know that the length is 100 feet more than the width. And what we want to do is we want to find out the length, and the width of the building. So, for a building, we've got a length and we've got a width. We know that the perimeter, or the distance all the way around, is equal to 860. Well, if we add up the sides going all the way around, we get that the perimeter is equal to the length plus the width plus the length plus the width. Or, that means 860 has to be equal to, by gathering like terms, we get 2L plus 2W. The second statement says that the length is 100 feet more than the width. That can be interpreted as L is 100 feet more than the width, which gives us this system of equations. Well, if you notice, this system of equations is this bottom equation is really geared up for, it's got L solved for. So let's plug this bottom equation into the top equation. If we know that 860 is equal to 2L plus 2W, and we know that L is equal to 100 plus W, that means 860 has to be equal to 2 times 100 plus W plus 2W. Now, we're going to distribute that 2 across addition to get 860 being equal to 200 plus 2W plus another 2W. We'll gather some like terms and subtract 200 from both sides to get 660 being equal to 4W. Divide both sides by 4. And working over here, we get W being equal to 4 goes into 660. 1, 6, 5. 165. Once we know what W is, we can plug it into either equation. This bottom one's going to be a little bit easier, and we'll get the value of L out. Well, we know that L is equal to 100 plus W. We know that W is 165. That means L is going to be 100 plus 165, or we get L being equal to 265. So, the process was the same, regardless of the fact it was a story problem or not. We had to dig a little bit deeper to get the information that we needed, but once we set up the problem, we used the method of substitution. we got one of the variables all by itself. This one was done for us. We plugged the bottom equation into the top equation to solve for one of our variables. Then we took that variable and we plugged it into either of these equations. One of them was a little bit easier to work with, so that's the one we chose. Once we performed that substitution, we came up with the other variable. By and large, that is the method of substitution. Isolate a variable, plug it into the other equation, solve for your missing values. Your homework is already up on Blackboard, and shoot me an email if you guys have any questions. Thank you. Bye-bye.